Hello, I welcome you all. The problem reads the board can be adjusted vertically by tilting it up and sliding the smooth pin A along the vertical guide G. When placed horizontally, the bottom C then bears along the edge of the guide where the static coefficient of friction mu s is equal to 0.4. Determine the largest dimension D, which will support any applied force F without causing the board to slip downwards. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have a board that can be adjusted vertically by tilting it up and sliding the smooth pin A along the vertical guide. So when you tilt up this particular board, you can move it upwards freely and smoothly. It means there is no friction. Okay. On the pin A, as it is, on the pin A, there is no friction with this particular guide. And that's the reason why you can move it freely upwards once you tilt it up and vertically. And we are now being asked to determine the largest dimension D, which can support any applied force F. So we need to draw the free body diagram. So look at the top view, see the top view. Okay, so we're saying when we apply the force here, okay, when you apply the force here, you expect some reaction force, right? There, like that. Okay, so expect some reaction force there, all right, and then you expect some normal force there, okay, if we call this NC, and some friction force FC, like so. Okay, so we are going to expect something like this. All right, so this is what we want to draw right now. Okay, so let's draw that quickly. So we have a board. This board is something like this. Something like this. Great. Something like this. So we are saying, and then the pin, let's say the pin is somewhere here. Okay, and we have some reaction force there, like that. Okay, that we are going to call, let's call it AX. Okay, and then we have another reaction force there that we are calling, this point is C, this point is A here. Here we are having a normal force NC, and then we also have another force which is resisting this particular board to move downwards as we apply the force on top. We are calling this as FC. And then we have this force here being applied, which is F. And then we have the dimension from somewhere there to there. This is 6 inch. And then from that point to there, this point here, this one is 0.75 inch. Okay, and then we have this dimension here, this dimension from there to there. This is the D we want to find, from the pin to the other point of the lower end of the board. So this is the free body diagram, and these are all the reaction forces that we expect. So what we are going to do now is, so for this board, because we do not want this board to move anytime we apply a force, therefore we are saying FC itself, for the board not to move downwards once we apply the force, then FC must meet this condition. FC must be less than or equal to mu C times NC. Okay, so then we are going to just get the other condition, which is just equating it. So we'll say FC equal to mu C NC which is therefore equal to, our mu c there is 0.4 times nc. Okay, so we have this first condition. So with this condition, we are now going to take some moments, right? We are going to take moments, let's say about this point here. It's not really A. This point is not really A. Let me call this point, because A is where the pin is. Let me wrap this point. Let me call this point as E. Okay, calling this point E. So I'll take moments about point E. So I'll say summation of moments about point E equal to 0, anti-clockwise being our reference. Then I have minus F times 6 plus 0.75, which is 6.75. Then plus NC times D. What else? Then equal to 0. Okay. Therefore, our D here is going to be equal to 6.75 F divided by NC, which eventually is equal to, alright, I'll get back. So our NC, let's sum up again the forces in the Y. So we have summation of forces in the Y direction equal to 0. We need to replace those values later on. So in the Y we have FC minus F equal to 0, and therefore our F is going to be equal to FC. Alright, and remember, what did we say FC is? FC, we found it to be that, so we can replace it here. Okay, so this becomes equal to 0.4 NC. Right, so even if we are not going to use the summation of forces in the x direction, let's still write it down for the sake of information. So summation of forces in the x direction equal to 0. What do we have? We have NC minus AX equal to 0. Therefore, AX equal to NC. Great. So now let's get back to our work. We found that F is equal to FC, which is eventually equal to 0.4 NC. And we also found that D is equal to 6.75 times F divided by NC. Replacing the F here, we have the following expression. D will be equal to 6.75 times 0.4 NC divided by NC. NC goes, therefore we have D equal to 2.7 inches, right? So this is our final solution. So this is the largest dimension, D. So when you look at D is independent. The largest dimension D is independent of any applied force F. Okay. D is independent of any applied force F. Okay. That is the largest dimension, D. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and share my channel. Bye bye and see you in my next screencast.